Good morning, everyone. I'm excited to talk to you about my capstone. I think that if you have ever spent too much time, money, or effort going grocery shopping just to lose your hard work to a silent spill, a toppled bag, or an inferno of a car that made you question whether your food is still safe to eat, you might actually appreciate the smart grocery bag. My name is Phylicia, and I'm an IoT student. I'm new to the field of IoT, coming from social work and public health. I'm also a military spouse to an active duty Air Force officer. I'm a New Yorker, which could be why one of my favorite stress management activities is walking, but only in certain cities. Everywhere else, I get my steps in by wandering the aisles of grocery stores and bookstores. So my product idea came to me in part because I've spent a lot of the last few years in smaller cities and thus at grocery stores. So basically, the smart grocery bag was intended to help make sure that your groceries and any other temperature sensitive or fragile goodies that you're moving from point A to point B make it there in one glorious piece. I wanted to make a bag that helped me figure out whether my hot and cold bags are actually keeping my foods the right temperature and help me decipher thuds and other mystery sounds from the trunk, especially after stopping short, having more of a lead foot than I meant to, or making too sharp of a turn. To start our journey into how this bag was constructed, I have my original hand-drawn schematic as well as a fritzing diagram that show the main components that I used with a Photon 2 microcontroller. I had two BME 280s, one on the front of the board so that it could face and measure temperatures outside the bag, and another on the back of the board to measure temperatures inside the bag. I had an OLED screen to display messages and a latching button to power the device on and off. I also used an MPU 6050 accelerometer to detect falling and a water sensor to detect leaks or spills. The device can connect to Wi-Fi in order to communicate with Adafruit feeds, which are organized into one comprehensive dashboard. The Adafruit dashboard website is accessible via phone or computer. To actually construct the bag, I started with an inexpensive insulated shopping bag. I cut some acrylic for scaffolding and a base to make the bag sturdier and able to hold up the console that I plan to embed. I did that at Fuse. I 3D printed a console case and I used SolidWorks Bamboo Studio and a Bamboo 3D printer. And as you saw earlier, I attached my components to a solder board. Finally, I found some cotton fabric panels that I sewed to the bag to give it a bit of flair. So let's watch a video. Okay, so here are my initial flowcharts, and I drew these up on Lucidchart. I had to create multiple flowcharts to handle the various types of data that I wanted reported on the Adafruit dashboard. This slide shows some sample code focused mostly on the temperature reading portion of the project. This code defines safe versus danger zones based on USDA and FDA definitions. They agree that 40 to 140 degrees Fahrenheit is considered a danger zone, and food at that temperature can't be left out for more than 2 hours. 90 to 110 degrees is especially risky, so you really can't leave food out when it's more than 90 degrees for more than an hour. This slide shows how I set up my Zapier SMS alerts. When a certain value hits the Adafruit feed, it triggers Zapier to send a text with a link for quick access to the dashboard for more details. On this slide, I showed the Zapier for the bag falling, when there's a food temperature warning or when there's a spill or a leak in the bag. And this should just be a short video showing what that looks like when you get the message. It has a link to the dashboard. All right, so now a demo video.
Yeah.
Okay. So one thing I was especially nervous about with the way the console was designed was whether the in-bag BME would accurately read temperatures. To overcome that concern, I raised both BMEs off the surface of the solder board to give them a little extra space. I repurposed that mismatched 3D print case piece to try to create an additional barrier between the in-bag and outside-of-bag BMEs, and got a couple of different thermometers to see how the in-bag temperature readings compared. I was impressed to find that the two BMEs did successfully read different temperatures, and the in-bag BME readings were similar to the thermometers. In terms of future directions, this iteration of the bag uses a Photon 2, which requires Wi-Fi. I'd like to switch to a boron to take advantage of its networking capability. I think the bag will be even more helpful when you aren't so constrained by Wi-Fi range. I also want to create a version of the console that you can move between bags to know which bags are more appropriate for what you're shopping for or transporting. I think as is, this bag could be helpful for companies that deliver food and groceries like DoorDash, or maybe even catering companies. But in terms of alternative applications, I would love to see a version of the bag that works for picnics, camping, road trips, or moving long distances. And I think that would require heating and cooling capabilities. Brian also mentioned seeing the concept applied to help pet owners who have to leave their animals in the car, and that seems like a really interesting direction too. So many things to explore. I would really like to thank NextFlex for the opportunity to take this program. It, like Nicole said, has been really such a growth opportunity. I'd also like to thank Brian, EJ, and Jamie, and my cohort mates for all the laughs and support and everything else that it took to get through the 10 weeks. I would also like to thank the deep dive administrative and support team. So Monica, Esteban, and Sue, thank you for supporting us. So here's some contact information. Thank you.